I'll be talking today a little bit about planets around other stars and kind of our search for planets like Earth around other stars. So to get us started, here's a little schematic that's obviously not to scale of 4 planetary systems. And one of them is real, and we're pretty sure it's there. It's this one down here. This is the solar system. It's kind of a little sketch of the inner solar system, starting with Jupiter out here, and we have the 4 terrestrial planets. We have Mercury, Venus, Earth, and Mars, and some asteroids in Jupiter. And we all know and love Earth very much because we're on it. Each of these other systems are artificial systems that were created in a computer. And they have a lot of variety of them. So this one on the top right, in this one, this planet looks a lot like Earth. It's got about the same mass, about the same composition. Its orbit is very similar, but the planetary system as a whole looks a lot different. There's a whole bunch of little small, icy, Mars-sized planets in there. And the biggest planet in the system is only about the size of Neptune, which is 20 times less massive than Jupiter. In this system here, it looks a lot like the inner solar system. We have three planets, an asteroid belt, a big Jupiter-like planet. This guy right here has an orbit very similar to the Earth. Its orbit is such that its temperature is just about right for water to be liquid on this planet's surface. But because of an unlikely fluke, this planet's unlucky, and it actually has no water on it. So it's in the right place for water to be liquid, but it's got no water. So it's kind of an unlucky place. This system here is completely different than our solar system. We have a hot Jupiter planet. This is a gaseous planet very close to a star. Even closer is a very hot Earth-like planet, a very hot rocky planet. And then exterior to the hot Jupiter is an ocean planet. So I'll be talking a little bit about things we know from looking at other stars, and also things we know, or we think we know, from computer simulations. So here are the questions that I'm going to address in my talk. What do we know about planets around other stars? Those are called extrasolar planets. How and where do planets like Earth form? And when are we going to find planets like Earth around other stars? And which technique is probably going to win the race and find the first one? And before I get going, I always have to thank NASA, who have funded me for the past several years doing this research. So before we get going on extrasolar planets, I'll talk about the solar system, just so we all know what's going on. In the solar system, it's important to remember that the sun is 99.9% of the stuff. Most of the mass in the solar system is in the sun. And most of the rest of it is in Jupiter, this guy. And the solar system is very nice and well behaved in a certain sense. We have small rocky planets close to the sun and big balls of gas further out. And these big balls of gas are really big. Jupiter is about 300 times more massive than the Earth is. And just for scale, Uranus and Neptune are both about 15 or 20 times more massive than Earth. So the small rocky things on the close to the star and big gaseous things further out. This is kind of the thing we know and love. And it was a big surprise when we found planets around other stars, because they don't really look like this. What do they look like? First of all, how do we find planets around other stars? There are several different techniques I'll go through here, and I'll give you a few highlights from what we've learned using each technique. So the first one is the most successful. It's the radial velocity method. So what we're looking at here is a planet's orbiting a star, and you can see in this graphic that the star is wobbling in response to the orbit of the planet. And so we can't actually see the planet directly here, but what you can do with the radial velocity technique is look at the star, basically see the star wobble, and infer the presence of a planet on a given orbit because of the wobble. And 311 planets have been found using this technique as of today. And the key information you get using this technique is some idea of the planet's mass. You don't get the exact mass because that depends on the orbital inclination. If you see this kind of system face on, then the star is moving, none of the star's motion is towards or away from you. And that's what you can measure. You can measure the motion towards or away from you. So you get an idea of the mass modulo kind of the orientation of the planet's orbit. And you also get some idea of the orbital period and the orbital properties. So what have we learned about, stars around other planets? Well, first of all, they look really weird. Here in this graph, the yellow lines are the orbits of the terrestrial planets in the solar system. So they're nice, pretty circular, and they're nice concentric circles, basically. And these red lines are the orbits of 4 planets around other stars. They're not all in the same system, but they kind of show the diversity of orbits around other stars. First of all, there's some orbits that are really ridiculously close in. These are the hot Jupiters. These are planets that are so, we call them hot because they're so ridiculously close to their stars. Way closer than any planets in our solar system. And in addition, kind of the most striking feature is there's lots of planets around other stars that have very eccentric orbits, very elliptical orbits. There's still some that do have quite circular orbits like this guy, but a large fraction have these quite eccentric orbits. And that's kind of interesting because it's not at all like the solar system. And so kind of putting ourselves in context, the solar system's architecture with our nice concentric circles seems kind of unusual. And the number of cases we know of that look like the solar system are just a handful. Another thing is that the radial velocity technique is getting better and better. The best current instrument is down in Chile on a big telescope. And it can measure, on a star that's say 100 light years away, you can measure the speed of that star to an accuracy of about a foot per second. So you can see the star light years away moving at the speed of a slow walk, which is crazy. And so given that you can measure such slow wobbles of the star, that means that you can see smaller and smaller planets and detect those. And so just last summer, in June 2008, this system was discovered, and it actually has 3 what are called super Earths. Right? These are planets that are between, say, 5 and 10 times the mass of Earth. And none of them were found until a few years ago. And now more and more of these are being found because of the sensitivity of the instruments. So this is kind of one cool new discovery. We don't know exactly what they look like, right? This is just an artist's impression. Because we don't know how big they are. We only have an idea of their mass. We don't know how big they are. So how do we learn something about how big they are? Well, we can use a different technique called transits. So transits is kind of like an eclipse or something. There we go. So what we're looking at is, imagine you just stare at a star for months on end, and you're just measuring its brightness. If there happens to be a planet that orbits that star in just the right way, such that the planet actually crosses the disk of the star, then you'll see the brightness of that star dip periodically in time. And basically the magnitude of that dip is how much light from the star is being blocked by the planet. And so that tells you some idea of the planet's size. So if you happen to know the size of the planet, and then maybe you also have radial velocity information about the mass of the planet, then you can have some idea of what the density is, and therefore maybe some rough composition. And to date, about 50 planets have been seen in transit. There's actually one just announced today that I'll talk about later. So what have we learned from the transit method? Well, we've learned that planets like Jupiter can have a wide range of internal structures. So here's Jupiter and Saturn, and little slices through them, and what they look like on the inside. So Jupiter and Saturn both have cores, rocky cores, that are maybe 5 or 10 times the mass of Earth. And then the rest of it, most of them are gas, basically hydrogen gas. Now, planets around other stars, some of them look kind of like that, and some of them are kind of puffed up, like these two. In particular, this guy. This probably has a tiny little core, but it's puffed up. It's much bigger than Jupiter. And maybe this has to do with how hot it is. All these planets that are found by transit are the hot Jupiters. They're the ones that are very close to their stars. So they're very hot. So that might have something to do with puffing this guy up. On the other hand, there's planets like this one here, which is more massive than Jupiter, but it's actually about the size of Saturn. And instead of having a core that's maybe 5 or 10 times the mass of Earth, this guy has a core that's about 80 times the mass of Earth. So there's a lot of diversity in terms of the internal structure of planets. A lot more than we see in our solar system. Another thing you can do with transits is actually look at the secondary transit. So imagine we're looking at the system. So say we're looking from our telescope down on the floor here. We're looking at this planet orbit the star. When the planet passes right in here, that's when the planet is blocking the light from the star and we see a transit. Then the planet keeps orbiting, and back here we see the planet go behind the star. So when the planet's back here, we see the star, but we see no contribution from the planet. And so you can imagine what that looks like in terms of the brightness. is, the brightness of the star plus planet. Then you see the transit, where some of the stars blocked, and it's flat again. And then this little blip is actually caused by, we're not seeing the contribution that comes from the planet. And so the difference between these two blips is actually due to the light from the planet itself, mainly reflected light from the star. You have a question?
Yes. So when the star is passing there on the low, the planet is passing on the low end there, it's eclipsing a part of this star, right?
Mm-hmm.
As it's moving, let's say, up to the right, does it generate any light of its own, or is it all the light from the sun? And why wouldn't that first quarter be where the planet does not add any light? The planet
You're right. I mean, the planet would have phases in here, and so the actual brightness of the planet would change a little bit along this path. But that change is very small, and so clearly it's barely measurable. If you look really closely, you might be able to see some kind of indication of the phase in this curve. But that's very difficult to do. So at the moment, you're leading very well into the next slide, though. So a big discovery that happened last week, it's in this week's issue of Nature, is that the heating of a giant exoplanet was observed. And so the planet is on a very elongated orbit. Its eccentricity is about 90%, so it's very, very elongated. An orbital period of about 100 days. And what these guys did is they used a space telescope, the Spitzer Space Telescope, to observe this planet during this part of its orbit. So just kind of when it's coming from the really cold part and just approaching the star, just when it's getting heated up. And what they saw was that this planet was heated up by 800 degrees Celsius, so about 1,400 degrees Fahrenheit, over a span of 6 hours. So that's just crazy, right? That's way bigger than anything that would ever happen on Earth. And these images here show their model for what the atmosphere is doing. And basically, the transport of heat in the atmosphere is very efficient compared to on Earth. And it's really neat. These images show what they think that the planet would actually look like. And so this blue light is actually reflected light from the star. It appears very blue because the planet absorbs red light very efficiently, but not blue light. And this red light is actually thermal emission caused by the heat of the planet. And so this might be what this planet actually looks like. It's an interesting one.
Your previous chart had a scale on it. Was that
This one?
realistic? Yeah. I mean,
This-
isn't it like 1 part in a million or something like that?
This scale here?
Yeah.
Yeah. So no, this is from their actual paper. So
Oh.
given that this is a very big
It's a big
planet, very
planet.
close to the stars,
Yes, yes.
the drop is significant. It's
Yeah.
a couple percent.
It's not an Earthly.
No.
On this slide, you said they saw. Do you mean they inferred?
Yeah, they infer this, right? It's not, they're not sticking a thermometer into the planet, right? They're using infrared observations to figure out what's happening with the temperature. So another technique to find planets around other stars is direct imaging. And there was a big news release about this a few months ago. This is actually an image of the first triple planet system observed by direct imaging. And so all this crazy fuzz in here, what that is basically noise. And that noise comes from the fact that these guys are using clever optical techniques to cancel out the light of the star so that they can see these planets. Because even giant planets are about 10 million times fainter than stars. And they're very, very close to their stars when you see them from far away. So if you want to have any chance of seeing the planets, you have to come up with some clever way of blocking out the light of the star. And so the way these guys did it is called coronography, but I'm not going to go into the details. But this is kind of the noise that was left over. And these blips, they actually watched them for several years, and they saw them move a little bit in their orbits, enough that they were confident that they're really planets. And so these guys are each, several times more massive than Jupiter. But this is the first time that we've seen, in visible light anyway, planets clearly orbiting other stars. And so with this technique, it's also important to note that it's easier to see planets further away when you're looking at them directly and you're trying to cancel out the light of the star. And so on this scale, the Earth's orbit would be way in here. This guy here, the innermost planet is, I think, 15 or 20 astronomical units, where 1 astronomical unit is the Earth-Sun distance. So these guys are orbiting way further away from their stars than Earth. All right, and the last technique I'll just mention briefly for finding planets around other stars is called gravitational lensing. So what you're doing here is you're measuring the brightness of a star again. And so here's your source star. It's some background star on the other side of the galaxy. And another star, this guy right here, that has a planet orbiting it, happens to cross just between you and that other star. So what happens is, when you're lined up just right, that extra star can bend some of these light rays and basically increase the brightness, basically magnify the background star. And the presence of the planet, what that does is it adds a little blip on top of the signal. So if there was no planet here, just a star coming just along the line of sight with the background star, what you would see is brightness would just kind of be a nice smooth thing. But because of the planet, you get these weird little blips here and there. And if you do lots and lots of math, which I'm not going to do for you, obviously, you can figure out, something about the planet's mass and something about its orbital distance. And this technique is very difficult, but a few planets have been found now. And one very cool one was announced last year. These guys found a Jupiter-Saturn analog. So here's another schematic of the solar system. And to scale, this would be the other planetary system that was found. It's important to note this one was actually scaled so that this star is much fainter than the sun. And so this, on this image, they scaled the orbits of the planets to be at about the same temperature as Jupiter and Saturn rather than the same orbital distance. But it's pretty cool to find an analog like that. And so these are the kind of planets that are actually hard to find with the other techniques. And so gravitational lensing can find them. So in terms of what we've learned about planets around other stars, well, we have some idea of the statistics. It's still pretty hard because it's hard to find small planets. And so here's the mass of planets versus the number that have been found. And so it's easy to find the really massive guys. It's very hard to find these guys. So these are very incomplete, whereas these are complete. But if you look at the statistics, it looks like about 10% of all stars in the sky have planets like Jupiter orbiting. So big balls of gas. And planets like Jupiter that we could already have detected. About 30% of stars have planets that are maybe 5 or 10 times the mass of Earth, these super Earth planets that are very close in, that are close enough to their stars that they've been detected by that wobble method. And how many planets like Earth are found? Well, we don't know, but if we kind of assume that keeps going, then there's probably a lot. And so we can't see them yet. So, well, what can we say about them? Well, why don't we take a look at how they form and see if we can figure out anything from them. So where do planets form? Well, first of all, where are we? We're in a galaxy. So imagine this is the Milky Way. It's not actually the Milky Way galaxy because we're in it. So we can't take a nice picture like this of it. But this is the Andromeda galaxy, the closest big galaxy to us. And we think it looks a lot like the Milky Way. And if this were the Milky Way, we would be around here. We're about 2/3 of the way between the center and the edge, in the disk somewhere, kind of in an average place. Nothing too exciting. So where do planets form? Basically, they form where stars form. Where do stars form? They form in molecular clouds of gas. So without realizing it, you've all seen one of these before. Orion is up in the sky right now. This is Orion's belt. That's his sword. Kind of this bright little smudge there is the Orion Nebula. And that's one place where stars are actively forming right now. This is what it looks like in a close-up view. And it's hard to see. I'll show some close-up images in a sec. But in these clouds of gas, stars and planets are actively forming right now. And here's another famous Hubble Space Telescope image of the Eagle Nebula. They call these the pillars of creation, where these are other big clouds of gas where stars and planets are forming right now. And so if we kind of look in more detail, where is the action really happening? Here are some pictures of disks around young stars. And so the stars are all right at the center here. And you can't see them because all these disks are kind of edge on. So you can imagine that a whole bunch of gas and dust is orbiting more or less kind of in a pancake shape or something like that. And we're looking right along the edge of the pancake. And so all the light that's trying to get out of that pancake is blocked. And so that's why you have these dark lanes right here. The disk is kind of flared a little bit, And so it's easier to see the light on the outer edges than it is right in the center. And so right in this thin layer right here is where there's a really strong concentration of dust and rocky stuff. And that's where, you know, plants that are rocky are forming. And obviously from these pictures we can't see exactly what's happening, but what we think is going on, we can always use artist's impressions to illustrate. And so here's what we think is going on there, very roughly. So we think there's this disk of gas and dust, and small little pieces of dust are kind of colliding and sticking and growing, and eventually growing through many different steps into full-size plants. And you can see once plants are big enough, then they have enough gravity, they can do cool things like carve out gaps in this disk, and those gaps can eventually cause the plant's orbits to change through various processes. But this is what we think is going on, and this is where we think plants are forming. And this process is very complicated to go from kind of some parcel of gas in a molecular cloud through all these steps to a nice system of planets. Here's a list of some of the important physical effects that are going on. And I'm not going to go through these. I just want you to realize that I'm going to show you just a little piece of what's a really big and complex process. I'm just going to show you little pieces here and there of what's happening. Mainly I'll be showing you kind of the end states and just kind of skipping through these other steps because they're, I don't know, not as pretty in general. So, if we're interested in Earth-like planets around other stars, then which planets could have life? Right? Those are kind of the ones that we're most interested in. When I think about this, there's at least three things that come to mind in terms of what a planet would need to maybe have life on. And the three things are water in liquid form, some source of heat, right? The right amount of heat. If it's too much heat, you'll burn off your water, you'll fry everything. But kind of the right amount of heat, and some kind of building blocks of life. That's kind of what we need to have an Earth, around another star. So where do these conditions occur? They occur in a place called the habitable zone. So that's a nice word for, the zone around the star where everything is nice and happy, kind of like the Goldilocks zone in some sense. So the solar system's habitable zone is right here. The Earth's right in it. Venus is too hot. Mars is too cold. You get the idea. If the Earth was closer to the sun, then it'd be too hot. If it was further out, then it would be a snowball. But it's important to remember, the habitable zone is the place where the temperature is right for water to be liquid on a planet's surface. But it's also important to remember that you need to have the water. And this is actually the universal symbol of life on other planets. Or on our planet, for that matter. So, in terms of talking about forming a habitable planet that's got the right temperature and the right ingredients, there's kind of a catch-22 that comes in. So to be, to have water in liquid on the Earth, you need to be hotter than 0 degrees Celsius, right? Or 32 degrees Fahrenheit. To get water onto a planet in the habitable zone, you need to deliver it in the form of ice. And that's because in these disks where plants are forming, the pressure is really low, and water can only exist as gas or as ice. There's no liquid floating around. So it's much easier to get the ice on there than it is to get the gas on there, it turns out. But in these very low pressure environments, ice only forms when it's colder than about negative 100 degrees Celsius. So that means you got to be hotter than 0 and colder than negative 100 at the same time. And that doesn't really work. So what this really means is that the material that builds plants like Earth is probably dry. It's rocks. It's not ice. That's the stuff that the Earth was formed on. So how do we get any water on Earth? Well, what we do is, on this image, the Earth would be kind of in this zone, in the zone where rocky stuff is growing into planets. And it's only when you get far enough away from the star that the temperature drops below some critical level, and you can have some combination of rock and ice being formed into planets. So in order to form a planet at the right temperature, but also have the right ingredients, what you need to do is actually mix things up during formation. So as the Earth formed, it could not form only from this material. It had to form from kind of a mixture of things across different zones. And that's how you kind of deliver water from there to the Earth. And I'll show a movie of that in a second. So how do planets form? Not just where do they form. Well, like I was saying, they form in these disks. Here's a little cartoon version of a disk. It's colder further away. And so the stuff that you have to build planets out of changes in different zones. And like I just mentioned, the Earth is kind of in this metal and rock zone. So in the next couple movies I'm going to show, there are going to be a couple of slightly technical terms. There's going to be semi-major axis and eccentricity thrown around. So just so you know what I'm talking about, the semi-major axis is just the orbital distance, basically. It's the average orbital distance. And the eccentricity is a measure of how elongated an orbit is. And the reason that eccentricity matters when you're talking about planets forming is that imagine everything had an eccentricity of 0. That would mean that all you had were concentric circular orbits. So imagine you're trying to build a planet. Right? You need things to collide. Right? If you have a bunch of rocks on these types of orbits, they can never collide because they never cross. But if you just take one of them and increase its eccentricity, then its orbit crosses the orbits of other ones and you can gross them. So that's why we care about eccentricity. So here's the movie. Eccentricity, semi-major axis. So the sun is here at 0. Jupiter is actually included, but you can't see it's out here at about 5.5. And what we're going to watch is over the period of a couple 100 million years, the time's up here, we're going to watch some small rocky things grow into full-size planets. And these are color-coded by their composition. So very close to the sun, they're dry, that's red. And further out, they have some water, about 5% water. And so we're just going to watch things grow in this disk of rocky stuff. So here we go. So there we go. You can see things grow faster, closer to the sun, and slower further out. But Jupiter's effects are noticed very strongly because of it excites basically the stuff out here at a few AU. By this point, let me just stop for 1 sec. This guy right here, pay special attention to this guy. That's going to turn into the Earth. But you can see after 8 million years, it's almost the size of the Earth, but it's still dry. Right? So you'll see it'll take a little while, but when the color of these guys change, that means that there's some kind of mixing between these zones that's happening. So when this guy goes from red to yellow to green to blue, that means it's getting hit by material that started out here that has some water, and that's basically delivering water to the Earth as it happens. So here we go. It's going to speed up in a sec just so the movie doesn't go too long. And you can see it's still pretty dry, and boom, it just changed color a couple times. Right? So water is just being delivered. And you can see that this phase of planet formation is very chaotic. There's things flying all over the place. And it takes a while for planets to carve out their little zone and for things to settle down. By about this time, by about 100 million years, things are more or less in their final state. In this particular simulation, I'll stop it now, we ended up with 3 planets. These 2 are pretty good analogs of Venus and Earth. And this one's not quite Mars, but it's close enough. So this is how we think planets are formed, by collisions of smaller bodies in these disks. And the way we think Earth got its water is from collisions, basically from water delivery of material that started further out, further away from the sun, and then eventually collided with Earth.
In these simulations, are you also doing the outer, of what would be the outer solar system?
No. We have to concentrate on one specific problem because they take a long time. This simulation took more than a year to run. So we can't just go and include everything because it just takes too long. So now what happens if we change things just a little bit? Right, so here's a solar system down here for scale. Now what if we run a bunch of simulations and change things just a little bit and see, what would be different on Earth if Jupiter were in a slightly different place or more massive or less massive or whatnot. And so here's a few examples. So a solar system for scale. In this case, Jupiter was only about the size of Saturn, which is about 1/3 of the mass of Jupiter. And it turns out this guy formed a very water-rich planet. This thing has maybe 5 or 10 times more water than Earth, and it's about 3 times the mass of Earth. This is the unlucky system that I talked about earlier, where we formed a planet in the habitable zone that didn't get any water. So it's this unlucky planet that has the right temperature for life, for water to be liquid on its surface, but it's got no water. So that's a really unlucky place. And this is one where there's no giant planets, really. The most massive planet in the system is only 10 Earth masses, so you might call it a super Earth or a Neptune-like planet. And so its gravity was much weaker during the formation process. And so instead of kind of carving out the asteroid belt here, you ended up with a bunch of planets in the asteroid belt. On the other hand, this planet right there looks a lot like the Earth. So that planet looks like the Earth, but the system as a whole looks a lot different.
Do all of these systems stabilize to circular orbits?
They end up on, it depends systematically on the giant planets. And so we can make them, basically we can reproduce the solar system, I mean the terrestrial planets' orbits pretty well. But we can't get every detail right, but we can do a pretty good job reproducing Mercury, Venus, Earth, and Mars. But when things are different, then things are different. So for example, one key thing is the eccentricity of the giant planets. So say you have a system like the solar system in terms of having a dominant planet like Jupiter. If Jupiter has a nice circular orbit, then the Earth right here is doing fine and it can receive lots of water. If, on the other hand, Jupiter had a more eccentric orbit, then to scale it would look like this, and this would be the Earth's orbit, and the Earth would probably be smaller and drier. The reason for this is the source of water on Earth is that kind of that outer material that probably started at around where the asteroid belt is now. That stuff is closer to where Jupiter is. So if Jupiter's orbit were more eccentric, then it would basically perturb the orbits of that material more strongly and prevent it from delivering water to Earth. Now changing gears a little bit, instead of systems that are very similar to our own solar system, what about hot Jupiter systems? So hot Jupiters, remember, those are giant planets very close to their stars. But we think that they formed further out and migrated inward. And the reason they migrated inward is because basically they had interactions with the gaseous disk. And the disk can push them around and usually tends to push them inward. And it pushes them in right through the zone where planets like Earth are trying to form. So can you still have planets like Earth in these systems? Well, it's time for a movie. So in this case, it's the same as before, but the x-axis is on a logarithmic scale. Okay, just so we can see what's going on very close up. So the giant planet here, Jupiter, is migrating inward. And what does it do? Well, it uses these specific places. These are called mean motion resonances with Jupiter. In this location, the orbit of one of these little guys is exactly half of the orbital period of the giant planet. And here it's 2/3. And so basically, as this giant planet migrates, it pushes this material interior to it. So it pushes about half of this material interior to its orbit as it moves inward. And about half gets a little too close and gets thrown out. And gets chucked out on these very, very eccentric orbits. So if we're interested in planets like Earth, then we're curious about what happens to material around 1 AU. So we want to know what happens to all this material. So let's look on a longer time scale. So now instead of going for 100,000 years, this movie will go for a couple 100 million years. And you'll see that the migration will be a little faster. So here we go. And you can see over time scales of about 1 million years, that scattered material has their orbits recircularized. And you have kind of a second phase of planet formation that looks a lot like what would happen if there was never this migration. Things get crazy, chaotic, and it takes a long time for planets to form, but they still do form. So, oops. Oh, there we go. I'll stop it right there. So at the end of this simulation, we have the hot Jupiter. Even closer in, this planet was kind of shoveled interior to the giant planet as it migrated inward by those resonances. This guy's about 4 times the mass of Earth. This one out here is the more interesting one. Its orbit is about 0.9 astronomical units. So its orbit is pretty similar to Earth's. Its mass is a little larger, it's about 3 Earth masses. But it has about 30 times more water than Earth. And the reason it does is because while the giant planet migrated inward, it really stirred up everything out here. And so a lot of that really water-rich stuff that started out here ended up in the habitable zone in there. So what might it look like on this planet? Well, we had someone draw it for us. So here's an image of maybe what it would look like. Right? It would probably be covered in oceans. It would probably be a water world. And you'll notice it's sunset. Sunset's always the best time for these kind of images. It's just so you can see here's the hot Jupiter, and it's plausible to think it might have rings. Even closer, you can just barely see that's that really close and hot super Earth planet. And on the Earth, storms tend to get really big over water, and then they kind of peter out over land typically. And so on a planet that's all water, you could end up with really big storms potentially. So here's a really big storm. But it can't block the view, right? It can't block the sunset, so it's just coming in at just the right time. And actually, an interesting story is one of the co-authors on this paper is a big blogger. And it turns out that the most popular science blog on the web is by a marine biologist guy who loves octopuses and squids and stuff. And so he had us do another version of this image with some life that might exist in there. And the only purpose for making it squid-like was because he wanted to get on this guy's blog. And it worked though, actually. We got on the blog.
How do you establish the initial conditions to start there? I mean, mass distribution of elements.
There's a huge number of models for that we use, and we also try to tie it into what we think was the case for the solar system in early times. I could talk in great detail about that, but basically we tie it into the best models that exist right now. All right, so now we've seen what Earths might look like from formation models. You know, when and how are we actually going to find these things? Well, I think the best candidate is still the radial velocity method. So remember, that's watching the star wobble in response to the planet. Here's the mass of planets that were found as a function of when they were found. So the first one was actually 1989, but it wasn't really confirmed until recently. Typically, people attribute this one in 1995 by the Swiss group to be the first planet found around a sun-like star anyway. And you can see since then, more than 300 planets have been found. And kind of the mass of these planets has been going down. Kind of the least massive planets have been decreasing. You know, sort of linearly maybe. And so if you keep extrapolating this out, you know, Earth's down here. Maybe in a couple of years, this technique could work. And it turns out that the least massive planets that have been found with this technique are about 4 Earth masses. And that's not exactly known because that still depends on the inclination angle, right? The actual orientation of the planet's orbit. So they could be slightly larger. But since they can measure the speed of stars to foot per second accuracy, I think that within a couple of years, this method's probably going to win. Here was a press release from last year, 2 years ago now, about the most Earth-like planet yet. It's called Gliese 581. And I'm running out of time, so I won't go into too much detail about this, but be careful when you see Earth-like out there in terms of news releases, because how Earth-like is this thing? And so here's what this planet looks like. This system is, the star itself is called Gliese 581. It has 3 planets. The one that they were talking about is the one called planet C. It just means the second one out. And so here's to scale this planetary system, Gliese 581, in the solar system, kind of the same temperature scale again. So what you can see is this planet that was being called Earth-like is much, much hotter than the Earth. Because if it was the same temperature as the Earth, it would be around here. So it's actually about 50% hotter than Venus. So this planet is quite small. It's one of the least massive planets detected yet. But it's still not really Earth-like because it's just too hot. So I think this system shows that if this planet had been a little further out, they probably could have found it. And so in some sense it was a little bit unlucky. But it's not really Earth-like, I don't think. So how else might we find Earth-like planets? Well, there was a big discovery announced today. I don't know if any of you saw it. It was announced by the CoRoT space mission. What that is, it's a satellite that's looking for transits. So it's similar to the Kepler mission. It's not actually nearly as advanced as Kepler, but it got there first. It was launched a couple of years ago. So what this satellite found and just announced today was a planet that's 1.7 times Earth's size. So remember, they saw the transit, so they saw how much light was blocked by the star, by the planet. And so they know the size really well. What they don't know very well is the mass. The mass is uncertain by about a factor of 2. It's somewhere between about 5 and 10 times the mass of Earth. So they don't know exactly what its density is. But at least in the press release, they were fairly confident that it was either a rocky planet or maybe an ocean planet. But they didn't think it was a gaseous planet, so they're pretty confident that it's probably got a solid surface. So this is the first planet detected around another star that they're, hand-wavingly confident has a solid surface. And it's not a very good place to live, because the star is pretty similar to the sun, and the orbital period of this planet is 20 hours. So a year on this planet is 20 hours. So it's a little hot for us, but it's still a pretty neat discovery. And of course, some other upcoming missions that might find planets like Earth, and that certainly will, are like the Kepler mission that's actually being, the data center is just over there. That's being launched on March 5th, I think. And the goal of the mission is to figure out what fraction of stars have planets like Earth. So I'm running out of time, so I'll go a little faster. Another mission that's centered at CU is called the New Worlds Observer. It's not certainly going to happen yet, but it's a cool idea. The idea is really simple. So it's trying to directly image planets around other stars. They want to fly a little telescope, actually a pretty big telescope, put a star shade and a occulter with this particular shape. It's actually about 50,000 miles between the star shade and the telescope. Not in orbit around the Earth, actually in orbit around the sun. And then here's your star, and here's your planet orbiting that star. And the properties of this star shade are such that it can make a really deep shadow. And even though this planet, if this is Earth, it would be actually about 10 billion times fainter than the star, very close to the star. But this star shade can create a very deep shadow that's very well behaved. And so they think they should be able to see the light from the planet and block the light of the star. Actually, they think they should be able to see it well enough that they can watch this planet for a long period of time and actually try to characterize it. Try to take a spectrum of it and see what it looks like. See if it has an atmosphere, see if it has water or ozone or that kind of thing. And one interesting thing you could do with that is if you stare at a planet like Earth long enough, you can get some idea of the properties of its surface. So on Earth, for example, if you're looking at Earth orbiting another star, the brightness of the planet goes down and up as the world turns. Right? And so it actually gets brightest right when the Sahara comes into view, because the Sahara is very reflective. And then it's actually, this blip here was the Pacific Ocean. And so if this is what you observe, you can make some clever assumptions and get some information about the surface of the planet itself. So before I finish, here's some kind of speculation about how many planets might be out there. So, big questions. How many planets are out there? Is there life on one of these planets? Well, we don't know. One way to think about this is to think on a very big scale. And the Hubble Space Telescope took this image several years ago that was kind of one of these wow images that I'll show you in a sec. What it did is stare at a blank patch of sky in the constellation Eridanus for about 15 days straight. So it took a picture with the camera, left the shutter open for 2 weeks straight. And here's what it saw. It saw this. This is a star right here. The ones with little crosses, these are stars. Every other little blip that you see there is a galaxy. Right? It's a galaxy typically millions or billions of light years away. Right? Every little blip you see. It's crazy. So if you're thinking kind of in a cosmic context, well, in our galaxy we have a few 100 billion stars. From images like this Hubble Deep Field image, we think there's a few 100 billion galaxies in the universe. That's a lot. Right, so how many planets are there? Well, we don't know exactly how many, what fraction of stars have planets, but maybe there's quintillions of planets out there. I think there probably are, right? This is a pretty big number. And we only know a few hundred right now. But I suspect that there's a lot out there. And what do they look like? Well, maybe they look something like this. Right? Here's some information from observations and from computers. Right? We got our solar system. Here's that planetary system, Gliese 581. Right? This is that unlucky system where this planet is about 5 Earth masses, but it's too hot. It's Earth-like, but it's really not. And other systems that we think are out there that we can't see yet include systems where you would have diversity of planets like Earth, both in terms of what the planets themselves look like, what their orbits are, what their compositions are, and what the planetary system as a whole looks like. And you can even have some of these crazy things where you have hot Jupiters and these ocean planets further out. So we think they're out there. So just to conclude, here's a few take-home messages. First of all, planets are everywhere. There's 337 known as of today, and I'm sure that number will keep going up very quickly. Our planet formation models predict that there should be lots of Earths out there. There should be a lot of diversity in terms of what we see, you know, how much water there are, and lots of exotic configurations. And I think that planets like Earth will be found in the next couple of years, and I accidentally skipped ahead to my last slide. So if you want any more information, actually maybe I'll just go back for a second. So this is my last point, just planets the size of Earth will probably be discovered in the next year or two. I think by that radial velocity method, but it could be a transit as well. We'll see. And so if you want any more information from me personally, you can email me or look at my website. And these other links are just kind of general extrasolar planet links that have lots of information, lots of pretty pictures and movies and such. So thank you for coming.
Students, run away. If you are here for extra credit and you know your teacher needs you to sign in, Therese downstairs has a sign-in sheet. Sean can answer some questions from the audience.
Question?